Oh, yeah. I clicked reply all.
All right, so this one. It's a parabola. And it's going to open upward because our a value is positive. And it's also 1. And if it's going to open upward, we need to find the lowest point because that'll be our vertex. So to find that is difficult in this form, standard form. But if we get it into vertex form, aptly named, it'll be easy to find that vertex. To do that, we want to complete the square. So Alvin, you know we're going to need a 2 there. 2 times 2 is 4. We don't have a 4 here. So what we'll do is we'll add 4 to both sides. This 4 is contained inside of this. And if we add a 4 to this side, then it all balances out. We have not changed the problem. There's still a minus 5 here. And there's a y plus 4 on this side. To subtract the 4, we get y equals the quantity of x plus 2, quantity squared, minus 9. Now think about this for a second. If we want to find the smallest possible value for y, which is the bottom of this, we need to make this as small as possible. Well, the smallest we can make this, the thing we actually have control over, is 0. Because it can't be negative, it's going to be squared. So unless we use imaginary numbers, 0 is as low as we can go. So x needs to be negative 2, because that'll make that whole thing 0. And then 0 minus 9 gets us our y value, which is negative 9. So that's our vertex. That's the lowest possible value we can get for y. And how do we get it? We plug in negative 2 for x. If we go to graph this, negative 2, negative 9 is this away. 1, 2, and down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Make sure you label your points. We know it's going upward, so I'll put the label below it. If you label it correctly but put the dot in the slightly wrong spot, I'll go with the label, right? Might save you. Although I'm not too particular. Negative 2 comma negative 9 is our vertex. We know this one's going to operate just like a normal parabola because its a value is 1. And by normal, I mean the parent function. This guy. All the 4 and the negative 5 do is kind of shift its starting location, its vertex. The a value determines its behavior. So it's going to have normal behavior. Normal behavior when we have x of 1, 2, and 3 is to get a y value of 1, 4, and 9. They're squares. So instead of starting from here, like this one would, we're going to start from here. 1 to the right gets us 1 up because 1 squared is 1, and of course it's symmetrical. 2 to the right gets us 4 up because 2 squared is 4. And 3 to the right, again, going back to our vertex, 3 to the right would normally get us 9 up, and this is a normal parabola. Oh, whoops, that's 4, not 3. Move. Counting is hard. Here's 4, 5, 6, 7, 8, 9. Ooh. Right on the y-axis, which makes sense. So, great question. I know that this is going to operate like a normal parabola because the a value is 1. And so here's what a normal parabola does. 1 gets 1, 2 gets 4, 3 gets 9. 1 gets 1, 2 gets 4, 3 gets 9. Is that making sense? 1, 1, 2, 2, 2, 4, 3, 9. Yeah, it's going to be just like our parent function. It's just moved around. That's it. Now, on the next one we're going to do, it will grow differently, and you'll see why. Okay, so completing the square, and then graphing after that, right? It's like it builds on itself. It's all connected. Yes, we're going to do that in quiz 5, correct? Yep. So now we're looking at graphing this. This one's going to open downward because our a value is negative, right? And it's going to open down twice as fast as a normal one. So let's talk about normal again. Normal does this. 1 gets 1, 2 gets 4, 3 gets 9, right? Because normal is this relationship. This one, right? So this one's going to move down twice as fast. So instead of getting 1, 1, it'll get 1 down 2. Does that make sense? Twice as much in the negative direction. 2 normally gets 4, but it's going to get negative 8 here. 3 normally gets 9, it's going to get negative 18. It's growing much faster. And you'll see that when we apply it. So that's normal. What we're going to get is all of these doubles and, of course, negated. Let's find our vertex, because that's important. We do that by completing the square. So if I complete the square here, first thing I need to do is get rid of this negative 2 in front of it. So I'll divide everything by -2. So I get y over -2 equals x squared minus 3x plus 7/2. And that looks nasty, but trust me, it won't be. It'll be fine. Just dividing everything by -2. Now I can complete the square. And it's kind of gross, because this is an odd number. Half of 3 is 3/2. I like using 3/2 better than 1.5 because 3/2 squared is very easy to do, whereas 1.5 squared takes a little bit of thinking. Side note, 3/2 squared is this, 9/4. So the number I need to add to complete the square is 9/4. So I'll add 9/4 to both. This is all contained within here. That's why I did it, so I could make this into that, making a perfect square. And of course I have to add 9/4 over here. Cool, cool, cool. So after I do that, all that's contained in here. I still have a plus 7/2. And I have y over -2 plus 9/4 over here. Now before we go subtracting that 9/4 on over, why don't we multiply everything by -2 so we can get rid of all these fractions? Works for me. If we do that, what we're going to get is, timesing this by -2 is -18/4. That simplifies to -9/2. This just becomes y, because that's why I did it. Timesing by -2. If I times this quantity by -2, I get this. No, it does not distribute. We talked about that before. And then timesing this by -2 gets us -7. We are nearly done. We want y on its own, so let's add 9/2. How many halves are in 7? 14 halves. So we have -14 halves, and we're adding 9 halves. That's going to get us -5 halves. So simplifying this, we're going to get y equals -2 times the quantity of x minus 3 halves, quantity squared. And then we're going to get -5 halves. Let me make sure I agree with what I am saying here. -14 halves, adding 9 halves, we'll have -5 halves left over. Oh, for sure. Well, you know I'm gonna like scan this and print it for you, right?
Yeah, I know.
Okay, good.
But I would like to point out.
Yeah, I told you. So a lot of little Algebra 1 stuff going on here. Commie denomies, multiplying to get rid of denominators, all that jazz. Timesing numbers, timesing fractions, across. So here we are. Now let's think about our vertex. Our vertex is going to be the number that makes this as small as possible. And the smallest we can make this is 0. Small, it's negative, but you understand. If I want to make this 0, I need x to be 3/2. And if I plug in 3/2, everything goes away except -5 halves, so y is -5 halves when I plug in x for 3/2. So there's the vertex. So let's find 3/2, -5 halves. 3/2 is here. And -5 halves is just out of screen, so I'm going to go down. 2 halves, 4 halves, -5 halves. Yay. And let's label that point so we know exactly where it is, just in case you put it in the wrong spot. 3/2, -5 halves. Now, from here, the other points we kind of get for free. We know that it's going to behave like this, except it's going to go down twice as fast. So instead of going 1 to the right and 1 down, we're going to go down twice as fast. So 1 to the right and 2 down, which puts us about here, right? And it's symmetrical. Instead of going 2 to the right and 4 down, what we're going to end up doing is going 8 down, twice as far, right? So here's 2. 3, 4, 5, 6, 7, 8, and of course it's symmetrical. And then instead of going 9 down after we go 3 to the right, we're going to go twice as far. That's 18 down. I'm going to run out of room for that, so I'm not even going to graph it. But I could put another point that is 3 to the right and 18 down if I wanted to. There is your parabola.
Did you go 2 to the right, 8 down?
Yep, 2 normally gets 4, because 2 squared is 4. So 2 is going to get 8 here. Does that make sense? Twice as far. It asks about the axis of symmetry. Our axis of symmetry is vertical. I often forget about this part of the question. You might as well. I'm lenient. However, for learning's sake, the equation of this line is this. X equals 3 halves. Because that's where all the points have x equals 3 halves. 3 halves 0, 3 halves 1, 3 halves 2, 3 halves 3. So that's our axis of symmetry. So this one's as weird as it possibly can get. We've got it going down. We have an odd number for our middle term, right? That's going to be a pain to divide with. We have a vertex that's in halves, so that's kind of a pain to graph that a little bit. So, a little weird. Turn the page. Looking at Pagina 3. It says, graph these equations. Good news. They're already in vertex form. The bad news is, one of these is not like the others. How are these going to differ if one's y equals and one's x equals? Yeah, we're going to minimize what y is, or maximize it, which means up and down. Whereas this one, we're going to affect x, so it's going to go left or right. So let's find the vertexes really quickly. Be careful when you're doing this. So what value of x is going to make that as small as possible? 3. Because as low as we can go is 0. Technically, it's as high as we can go because we can get negative numbers, but whatever. And if we plug in 3, what do we get for y? Well, negative 4. Because 0 minus 4 is negative 4. Over here's where the danger comes in for a lot of you. Notice if we want to minimize this, we're plugging in for y. What should I plug in for y to make this 0? 3. For y, not x. Now, when we do that, this becomes 0 minus 4, which is negative 4, and we get that for x. Are they always going to be flipped like that? Not always. I purposely made this one so it would be that way. Make sure you have your brain on. You'll be all right. So here is our vertex for the one that's going up and down. In fact, this one's going down, correct? Down twice as fast. So let's find our vertex. 3, negative 4, 1, 2, 3, 4. And it's going down, so I'll label it like this. And it's going down twice as fast. So from our vertex, instead of the 1 to the right, 1 down, we're going to go 1 to the right, 2 down. Instead of going 2 to the right and 4 down, we're going to go 2 and 8. 2 gets us 8, 2, 3, 4, 5, 6, 7, 8. And once again, I don't have enough room to go down 18 if I went 3 to the right, but, you know, you can imagine. It continues on. So there's our first parabola. Our other one is moving to the left because it's either left or right, and left is the negative direction, and it's going to move twice as fast as a normal parabola. I'll do this one in green. Negative 4, 3 is its vertex, and that's right here. And it's moving to the left twice as fast. So instead of 1, 1, we're going to get 1, 2. Again, up 1, left 2, because we're moving to the left. 2 normally gets 4, but it's moving twice as fast, so 2 is going to get 8. 3, 4, 5, 6, 7, 8. And of course, 9 is normally what we get next, but it would be 18. And we don't have room for that. These are the same parabola. In fact, all parabolas are mathematically similar. It just depends on how much you zoom in or zoom out. Even if they're really wide or really skinny, they're all actually the same. And by same, I mean similar. This is a 90-degree rotation. Either clockwise or counterclockwise, doesn't matter, because this would be clockwise, or sorry, counterclockwise, this would be clockwise. No one's telling you which way we're starting and which way we're ending. There is no A and A prime here. So I'll just say clockwise. I'm not super particular about this stuff. I often forget that's even part of the question. But hopefully you realize they're the same thing. The last of the basic questions. What, we're already done with the basics? I know. This one ain't a parabola. And you know this because x and y are both squared. It's going to be a circle, and that's because the terms in front of the coefficients, I should say, in front of x squared and y squared are both equal. They're both 1 in this case. If they were lopsided, like that was a 3 and that was a 5, it would stretch it strangely. We end up with an ellipse. You'll learn about this next year. So, first thing I'm going to do, just to make things look a little bit more kosher, is I'll write my x's next to each other, which is never a good idea in real life. And then we'll have our y's next to each other. Just so I can point out this with my pink eraser, and I'm not sure where this came from because I only buy the nice ones, but I have a pink eraser. If I were to cover up the y's, I think you would agree we could complete the square here, right? We need x minus 5 quantity squared. If I were to cover up the x's, I would need y plus 2 quantity squared to complete the square. We're going to complete the square twice. This is going to find us our center, which is the most important point on your circle. This is going to get us x minus 5 quantity squared. But of course, this ain't that. It would be if there was a positive 25 attached to it. Ah, now this is that. And over here, y plus 2 quantity squared would be this if there was a plus 4 on the end, because 2 times 2 is 4. But in order to accomplish this, I'm going to have to add 25 and 4 to this side, aren't I? Aren't I? Which is nice, because what am I going to get over here? 49. Which is a square number, which is nice, because remember what this represents. This is distance formula. It is telling you that the distance between this point and any point will always be the same. It'll always be 7. Because again, Pythagorean theorem is a squared plus b squared is c squared. C is the distance, not c squared. So 7 is our radius. It's actually a nice number.
Can you pause for like 2 seconds?
You just read it, Mr. Mac?
Yeah. And it's because this is a squared plus b squared is c squared, and the distance is c, not c squared. That's our radius. Distance is c, not c squared. So it's the root of whatever this is. In this case, it comes out nicely. Radius is 7. That means our center is going to be this. Think about this. This means the distance between this point and any point will always be 7, right? That's what we're saying here, essentially. And that's what a circle is, right? The same distance between a single point and any other point. The center would then be a distance of 0 from itself. So we don't want the distance to be 7. We want this to equal 0. So what would I have to plug in for x and y? I'd have to plug in 5 for x and negative 2 for y to make this a distance of 0. So that would be the point that's 0 distance from this point, meaning it's the center. 5, negative 2 exists in this quadrant. 1, 2, 3, 4, 5, negative 2. That's our center. So to graph our circle, we're going to go out 7 in every direction. So if I go 7 up, 1, 2, 3, 4, 5, 6, 7, up. Where do I end up? Well, I'm going to end up at negative 2 plus 7 because I'm going up, and that's going to affect the y value. So 5, 5. If I go 7 to the right, 1, 2, 3, 4, 5, 6, 7, I end up here, which is 7 more in the x direction. So that's going to be 5 plus 7, which is 12. Our height didn't change, though. We're still 2 below the x-axis. If I go left, 1, 2, 3, 4, 5, 6, 7. I'm now 7 to the left of 5, which of course is negative 2. And if I go 7 down, 1, 2, 3, 4, 5, 6, 7. I'm at 5, negative 9. And then we draw our circle.
Oh yeah. Oh yeah. Yeah, that's a really good circle. I admit, I wish there was. I have like a rhombus sculpt. Mine's like a square.
If you're not having fun, what are you doing, right?
Yeah. Shut up.
Complete the square twice, get your center. Radius is the root because a squared plus b squared equals c squared. There's a whole connection with Pythagorean theorem here that's been going on since pre-algebra, but if you haven't had the full story, you're coming in like part 4, it's okay, you'll be all right. Intermediate questions. Shall I continue or should I go to quiz 5? Just for you, Gage. All right, graph this equation. First off, caution, caution. This one's not going up and down. This one's going sideways. And we know that because x is the thing we're maximizing or minimizing. So we're either going to go far to the right or far to the left, just like American politics. So, are we going to go to the right or left? To the right, because it's going positive. So it's going this way. Just make a note of that before we start. Always think about it before we get going. It's going to the right. And it's going 4 times as fast. Oh my God. That's like almost too fast. So let's turn this into a problem we do understand. Let's get rid of the a value by dividing everything by 4, which will work nicely for the most part. Don't fear 9/4. There's nothing wrong with 9/4. Let's complete the square. I'll need 2. This is almost that. Except this needs a +4, right? So we'll add a +4, and we'll get away with that with some very clever algebra. That's all in the root, or in the quantity. I'll zoom in for those playing along at home. We still have 9 quatas. And now before we subtract 4 and get commie denomies, what if we just times everything by 4 first? Get rid of the denominators? We'll get 16 plus x equals 4. Don't forget that 4. Times the quantity of y plus 2 squared.
Can you pause for 2 seconds?
And 9. Yeah.
Yeah, I would.
Timesing everything by 4 makes it easier. We were going to have to do it anyway, so why not do it now?
Times it by 8.
That's my song. You can times it by 8.
Divided by 2.
And then, yeah, because x would be a 2, right? Yeah. Okay, stop. 64 or 64.
Yeah. Ooh.
Or -8.
Ooh. Or.
Wait, where did the 16 come from?
Yeah.
I timesed everything by 4 to get rid of the division.
Oh, okay.
And then after.
It's better than getting commie denomies.
Okay, you were
So
very fast.
you might subtract 4 and get commie denomies, but then we have to times by 4 to get x on its own, right? So I just times by 4 first. Do you see how 4 times 4 is 16? This times 4 divides out, we get x. This times 4 is this.
It would have been nice if you wrote that you were doing.
Okay.
Otherwise I get confused.
Yeah, you were going really fast.
Well, today is not meant to be a learning day. It's supposed to be a review day. So,
It's a learning day for me.
gotcha.
No one learned anything. Ever.
So, now we're here. If I subtract 16, we're going to get x equals 4 times the quantity of y plus 2 squared minus 7. This looks like our vertex is going to be the thing that makes this as small as possible. What value of y, not x,
-2.
-2, will lead us to a value of x, which is -7.
Wait, hold on. No, I was thinking about it. I know how to do that.
I don't know how to do either of those things.
I'm illiterate, actually. 4, 5,
Hi, YouTube. -7, -2. 1, 2, 3, 4, 5, 6, 7, down 2. Now we're moving to the right, so I'm going to write that over here. And how fast are we going to the right? Almost too fast, right? 4 times. So you agree, normally when 1 gets 1, but 1's really going to get 4 this time. 1 gets 4. Oh my God. It's going so fast. 2 normally gets 4, but 2's going to get 16. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And of course it's symmetrical. 3 normally gets 9, but 3 this time would get 36. Ain't nobody got time for that. Behold! The sideways parabola is moving to the right at 4 times the speed with the vertex -7, -4, -2.
I think this is the same numbers as yesterday.
It's not. Yesterday we had a weird route for the
Well then, if you knew
radius.
why you answer me.
Because I didn't know at first, but I know now.
You're a liar. You're probably the one who got the video age restriction.
All right, A and B, not so bad. It's C that's the one that's a little bit of a kicker. It says find an equation whose graph is a parabola with vertex 1, 2, and has a vertical axis of symmetry. Ooh. That means we're maximizing Y. If our vertex is 1, 2, that means our biggest value of Y is 2, and it comes when X is 1. So if X is 1, we know that'll minimize it, right?
And that means it has eyes too. Feel like
Plus 2.
drink something out of a toilet at a frat party.
Now, problem. This parabola does go up and down. It does go through 1, 2, but it does not go through 3, 3. Because check it out. If I plug in 3, I get 3 minus 1, which is 2. 2 squared is 4. 4 plus 2 ain't 3, it's 6. Oh, no. So how do we fix that problem? Well, 3 minus 1 is 2. 2 squared is 4. We get 4 here. If we want this to equal 3, we really want this to be a 1. 1 plus 2 gets 3, right? So if this is 4, what do I times it by to get 1?
Hold up. Mr. Mac, a quarter? Did both
A quarter.
get deleted or just one?
No comment.
Please comment.
1, 2.
Like, did
Therefore, it's open.
you would,
We recorded.
last night you did 3 to 6. And
Yes,
6
and
to
both
9.
those videos did not have sound, which is why we had to delete them and try again. So I have a recording here, and I have a recording there. I'm going to spend time recording extra stuff if you need to see extra stuff.
Oh my god.
I know. That's the danger. That's the danger.
Danger of what?
The danger of not being there live. I know, right? I did the best I could.
This is actually a lesson.
Yeah, it's not a lesson. It's just like, that's just life, man,
To
sometimes.
teach us a valuable lesson.
I can only do the best I can, just like you can only do the best you can. And that's always enough for me. So, 3 and 3 does go through this now, because we get 4 times a quarter, which is 1, plus 2 is 3. So there's our parabola.
I'm not doing that one.
For this one,
It's kind of weird.
find an equation whose graph is a parabola with this vertex. Okay, looks similar, except it's a horizontal axis of symmetry. So we're going to start with x equals, because we're maximizing or minimizing x. Yeah, that's the equation. Right, vertex is 1, 2.
Okay.
3, 3 works with it. That's it.
Okay.
Exactly, yeah, absolutely, right? Because it doesn't go through 3, 3 until we adjust how quickly it's growing. And that's what's going to get it through. So gauge, yes. So 3 minus 3, or sorry, 3 minus 1 is 2, correct? So 2 squared is 4. 4 plus 2 ain't 3. Right? But if I have 4 here, 4 times a quarter gets us 1. 1 plus 2 is 3. So it's a mystery to figure out what number is going to go here, right? We can't adjust this because that'll change the vertex. So we have to adjust how wide it's going to be. This one. Visualizing that? Okay. We're going to get another shot here, though. Okay? So this one. Vertex. 1 is x. Be careful about that. 2 is y. So if we plug in 2 for y, we should get 0, right? Here. And we'll get 1 for x. So I'll pause for station identification. If we plug in 2 for y, 2 minus 2 is 0. 0 plus 1 is 1. The question is, does it go through 3, 3? Spoilers, it doesn't, right? If we plug in 3, we get 1 here. 1 squared is 1. 1 plus 1 is 2, not 3. Darn. So notice when we plug in 3. 3 minus 2 is? 1 squared is? And you wish this were 2, don't you? 2 plus 1 is 3. I know. I know. Part C is the kicker. It says, is there an equation besides the ones we did before? that goes through 3, 3 and has a vertex at 1, 2? And the answer is yes. And let me illustrate this and why this might be.
But I'm not.
If this is 3, 3, hi YouTube. And our vertex is 1, 2. I'll do that in green. 1, 2. Well, that wouldn't be a good idea. So there's a vertex or a parabola that goes through them vertically. That's the one we found earlier. Notice it's pretty wide, which makes sense. It grows slowly. And we have a parabola that goes sideways. And notice it grows pretty quickly, which makes sense. Twice as quick growth, right? There is another, like Yoda said, with the Star Wars thing. In fact, there's infinitely many. Because the only reason we were able to find one here and one here is because we were restricted to vertical only or horizontal only. But what if we go at a diagonal? So Gage, another way we can do this is to go at a diagonal. That would be a parabola that goes through them. I'll zoom in. There are infinite many parabolas that go through that, between perfectly vertical and perfectly horizontal. So yes, there are more. And here's why. We can have sideways. Now you might ask, how do we get sideways? I know how to get, or like diagonal. I know how to get left to right. I know how to get up and down. That is a great question. You'll find out next year. That's why this is a diamond question. It's just getting you to think outside the box.
Stay on that for like
Mm. What is the equation of the pink one or the peach one? I don't know. I mean, I do, but we don't know yet. But it's getting me thinking. No.
no. Okay.
It says, is there an equation? Yes, there is. Moving on.
Well,
All right.
it's all back up and get home.
Do the circles that have these equations intersect when they're graphed on the Cartesian plane? Now, there's lots of ways to solve this. One way is to figure out where they intersect by using elimination or substitution. Another way is to just graph them and see if you get lucky. So let's do that. The center here for this circle is 1, 0, because 1 makes this 0 and 0 makes that 0. And the radius for this one is going to be what? Don't say 4. What's the radius for this one going to be? The root of 4. So if I were to graph this, 1, 0 is its center, a radius of 2.
Just got warm.
There's my quick little graph, okay? Sorry, I missed that one. That's going to be important. The vertex here, center, is negative 3, 0. And the radius for it is also 2. So negative 3, 0 is here.
Different.
You good?
No, it's
Is
not.
that funny?
Is it different? I forgot.
Yeah.
Now, if I drew this more carefully, where do they intersect? Looks like that point there. They're kissing. Aww. What is that point? Looks like negative 1, 0 to me. That's where they intersect. Meaning that if you had done elimination or substitution, you would find out that negative 1, 0 is a solution to both equations. Aw, they kiss.
Aww. That's so sweet.
Yes,
Is the 11th one, is that 4?
correct. It's the one with the rat.
Yeah.
That's how I remember it.
And then your mom's on there as well.
Got him. Shout out to Mom.
Michelle. Michelle's everywhere.
Consider this equation. What kind of thing is this going to look like? X squared, Y squared,
I have a question.
circle. Yeah.
When you record the videos, is it gonna be like this? Because if so, I might as well just not.
How can I help?
Oh. Well,
Right now we're doing intermediate quiz 6 questions. If you haven't got the basics down, the intermediates are going to be a little weird, which is why this isn't teaching time, it's review time. So, will it be like this? Yes, but it'll be the stuff you already know, which means it'll work better than the stuff that you don't know yet. Imagine teaching someone something they've never seen before really fast. Not going to work, right? But imagine reviewing with somebody really quickly something they already know.
Okay.
Maisie, you were here yesterday. Did we go quickly? Yes. But did it work? Okay. These are circles. So when it says non-degenerate, it means a real circle, not a circle with radius 0. So let's find out what the radius of this circle is going to be. Brianna, when I complete the square here, what number do I need? This number. Trick question. Yep. And I'll need +4 to make it work, right?
Yes.
When I complete the circle here, what number will I need? 3. Gage is impatient. And we're going to need 9. So, to be non-degenerate, we need a real radius. Means it can't be 0, can't be negative. K can be any number you want as long as it doesn't make this 0 or negative. What number would make this 0? Negative 13. So K has to be greater than negative 13. Because it can't be 0 and it can't be negative. 1424, a diameter of a circle. You know what that means, right? Then we don't need to read this. Here's our diameter.
That was really good. I only cried
Thank you.
2 seconds.
How big is our radius if that's our diameter? How big is our radius if that's our diameter? Half. And half of this is 15, correct? So if I go 15 away from both points, I end up here. That's our center. They want to know if this point is on the circle, x comma 15, where is it? Well, if I go 15 above, I'll get 10, 15. If I go 15 below, I'll get 10, negative 15. So it looks like the x we're looking for is 10. Always the answer. That's what I'm hearing. That's what I'm hearing. 10 is always the answer. Shout out to 10 in the comments.
Like Allen Iverson.
If you know, you know. That's right. Thank you, Scooter. And that's it for the intermediate questions. Now we're on to advanced, but let's not and say we did.
Yeah, I like that idea.
Best idea today. I won't have to force
Where's
a
my
smile to your
Chromebook?
breakfast because I'll be.
Hon, I think it grew legs and ran away.
I might have called under the door too.
Oh, I didn't
In a second. What?
My Chromebook disappeared.
I'm sorry for your
Does it look like
loss.
it can fit under the door, Mr. Mac? It does.
I don't think it could.
Under the
I don't know. It's kind of like mice, right?
That's probably what happened.
Why are we leaving